Good afternoon. Good afternoon. Yep. Good afternoon. Hello. Yep. Test. Yep. Good afternoon. I hope you are well and that you have enjoyed the lab session. What we are going to do now is basically make sure that you have understood what we have done and why have we done this. So, anyone knows what is going to happen next Black Friday? So no one finished the practical session? No one? Anyone? No? At what time? At what time? Okay, thank you. So you know now. So we can finish now. No. Well. So first of all, we have this amount of bits, and in the question it was says that it was intercepted in an iPhone 8. So how do we know the architecture of this processor? So basically what we do is, by the way, you have your chat here if you want to. Regarding the chat, there was something yesterday. If you put the word question in capital letters in order to differentiate from the other things, that will be good. So when you have a genuine question, you put in capital letters the word question, and if what you want to say is just a joke, you just don't put that, and with this I can differentiate if it is a question or not. So basically what we want to see is which processor has the iPhone 8. So, and we see here that it has an A11 Bionic processor. So next what we do is, what is the architecture of this processor? And then it's some place we have, for instance, here it has an ARM V8 architecture. So we have assumed that this is the same architecture that the one we are seeing in this module. But now I ask you, is the same architecture that we are seeing here? The ARM V8 instruction set is the same as the one we are seeing here? What do you think? So it's called the same? How do we call the instruction set we are seeing in this module? It's LEG V8, LEG V8. And if you remember, in the first lecture of this chapter, we mentioned we are going to use a subset of ARM V8. Why are we using a subset and not the real one? Because the real one is very complex, and for an introductory course, we just are using a subset. It will be similar to the one we are learning now. And it will have also a reference data. And right now you already know, if you understand how to use the reference data, you can encode instructions in zeros and ones and vice versa. So in this practice session, what we have assumed is that, okay, the iPhone is using the same architecture than the one that we are using. But that's not completely true. It was just for making it a bit more appealing. So now that we know the architecture, and surprisingly is the same as the one we are using here, we are able to, given this machine code, translate it into instructions, which is actually the next question. How do I translate this into instructions? I think that all of you know this, but I'm going to do one instruction just to be sure that you follow me. So I'm basically going to copy all the bits to any place, for instance here. And then, what is the size of each instruction? We know that the size of each instruction in this module is 32 bits. So basically, I'm going to split all the instructions in 32 bits. So this will be one instruction, this will be second instruction, third instruction, fourth instruction. Okay, the first thing I do is I have there just bits. I know that every instruction is 32 bits, but I don't know how is formatted each instruction, because we have seen different formats. So the first I do is, I know that the operation code will be the first part of the instruction. And I know that it could be 10 bits or 11 bits. And I also know that there will be no instruction with the same 10 bits. That means that if I look in all the operation codes, those first 10 bits will be not repeated in any other operation code. So for instance, here I have 100, 1000, and 100. And then I go to the here in the modules, you know that we have a wonderful reference data here. So one way of looking for this, for the operation code, is we have here, let me see if I can. So we have here in the second page of the reference data, we have all the operation codes here. So then we look here. Remember that we are looking for this operation code, 100, 1000, 100. So we look in those operation codes, and at some point I have here 100, 1100. So this code is not going to be repeated in any other operation code, even if it has 11 bits or 10. So now that I know that this is my operation code, I see, okay, this is an add A instruction. So now I know that this instruction, because of this operation code, is an add I instruction. Great. So now, here I can also see the format of the instruction. This I here means that this is the format of the instruction. So you can look the format of the instruction here. And here you see for instruction I, we see that the operation code is placed between bits 31 to 22. Then we have something called arithmetic logic unit immediate, then something called Rn, which is register N, and something called Rd, register D. So you can either look at this, or you know that in the slides you also have this with colors. So here, for instance, we have this instruction, and we have that the operation code is 10 bits. Then we have an immediate value which is 12 bits. So I just go here, I say, okay, operation code 10 bits. The next 12 bits, 1, 2, 3. The next 12 bits, those ones, is what we have here, an immediate value. Then we have register N, 5 bits. 1, 2, 3, 4, 5. And then we have another register, register D, which is also 5 bits. So with this we have 10 bits, 12 bits, 5, and 5 bits. So now I know that this is the operation code. This is the immediate value. This is register N, which means first register input, and this is register destination, which is where the result of the operation is going to be stored. Okay, so I know that the operation code is at I. Then for this immediate value, I have shown you how to convert this to decimal. There are different ways. One I have shown you is this one. We just go to the calculator. We select the programmer mode. And here you see we have hexadecimal, decimal, octal, and binary. If we select binary and we just paste here our value, we have that the equivalent in decimal of this number is 243. So now we know that this is 243. Then if we convert these 5 bits, again we move to binary, we clear, we paste this. In decimal this is 31, so this will be register 31. And then we do the same for the last register. So we switch to binary, we clear, we paste this, and then we know that this in decimal is number 9. So now, usually for immediate values, we put an X before it, a hash before it, in order to tell that this is a number. For registers, the convention is that we put capital X. So now, I have 2 registers here. How do I know what those registers are used for? For instance, I can go to the reference data, and here you have for each register what is it used. For instance, register 9, it's a temporary register, and in the case of the 31, is a constant, it has always the constant value 0, and it is usually referred to as XZR. So we are just going to use this. So now that we know the meaning of all the bits, what we do is, you can look this in the slide with colors. So you have here that RD goes in the first position, RN in the second position, and the immediate value in the third position. So here then we have that at I, the correct way of putting it will be xd in the first position, xn in this case in the second position, and then the immediate value in the last position. Is this clear? So basically, you need to do this with all the instructions. So what you will have in the final assessment, you will not have the slides. You will have anything you need from the reference data. So you need to learn how to use the reference data. So the slides with colors are good for the beginning, for starting decoding and encoding instructions. But once you are used to it, only with the reference data, you need to gather all the data from the reference data in order to convert one instruction. So if we do this with all the instructions, at the end we will have something similar to this code. And what we have done by converting matching code or matching language to assembly language is usually referred to as decoding matching language or reverse engineering. This is usually not allowed. So usually in the licenses of software, they tell you, okay, you are not allowed to do reverse engineering. Why? Because you will be able to reproduce that software, and if you need to pay for obtaining the software and you are doing this, is not legal. So you will have this solution on Canvas, and you will have also an Excel sheet in which you can check all the conversions. For instance, you can use whatever you want. For instance, here what I have done is, so I have one instruction, the arguments, I have the equivalent to that instruction in binary, I have the format of the instruction, and depending on each format, I allocate it differently. For instance, the I format, which is the one we have done, we have these fields. In the case of the D format, we have the instructions, and in the case of the R format, we have this other format. So you will have all this information on Canvas to help you to check if you have done this properly. Now that we know the code, we are going to interpret this code. So what we are doing here, in the first instruction, what we are doing is just making register 9 equal to, this register is 0 always, so we are making it equal to 243. And then what we are doing here is, I load a byte from memory, in this case byte 0, I apply an exclusive OR to that byte using register 9, which has this value, and I store again that value in memory. I repeat this with byte 0, 1, 2, and so on until the byte 12. So what comes now is just, you don't need to know this. It was just to make the session more interesting. So this is usually known in cryptography as a simple XOR cipher. When I say XOR, is the same as the EOR in OR instruction. So usually people calls the exclusive OR XOR, but here the authors decided to have the instruction EOR instead of XOR, but it's the same, an exclusive OR. So what this program is doing is, I have an input X, which is what I have in the array memory, and I have a key, and then I have the output, will be Y, will be an encrypted value. And this cipher is very simple, and for decrypting it, we just do the same operation, but with the same key, but by using the same operation with the same key, we obtain the decrypted message. Is that clear? So I have one input, I do exclusive OR with the key, which in this case my key was 243, and the result is the same message but encrypted. And for decrypting it, I do the same. I apply an exclusive OR with the same key, and I have the decrypted message. In order to use this program to exchange messages, we only need to share, okay, what will be the key we are going to use. By the way, so here we are referring to the exclusive OR by EOR, XOR, but sometimes when you program or when you see other mathematical notations, it's used this symbol here to refer to the XOR operation. So now that we know what the program is doing, we have the second part. Any question regarding the first part? So is the final assessment? The final assessment is multiple choice. That like the one you have for the first chapter, you will have a similar one for the second chapter, and it will be multiple choice. Yes, in this lecture we will see the solution for the practical. So in the assessment, what you will have is the reference data. You will have this, and here you can look for the format of all the instructions. You have here format R, this format I, this format. Okay. So you don't need to learn this. You need to learn how to use this information. So this question here, make sure that you understand this, because it will be something that potentially I will ask in the exam. Someone is asking, if at IE hexadecimal value is 4A8, how does it only have 10 bits in our instruction set? So here, for instance, I think we showed this slide yesterday, but if we go to the reference data, we see that at immediate has is blocking two operation codes, 488 and 489. If you convert those hexadecimals into binaries, you have this value and this value. And what we are doing here in order to have only 10 bits is keeping the common 10 bits of those two hexadecimal values or of those two binaries. And by doing this, there will be no other operation with this operation code. There will be no other operation with this operation code. So we are blocking two operation codes for only one operation. Why? Because we want to only to use 10 bits. This is something I will ask you in the exam. So please make sure that you understand this. And you see in the yesterday's slides you have this. So yes, hopefully this is being recorded. Okay, I think. So now let's go for the second part. In the second part, the new thing was we are now able with bits to do instructions and so on. But people usually don't use numbers. We use a language and we need letters. There are different conventions to use to convert bits into into characters. In this case, we are using a language called R3, which stands for, I don't know if you have here, for what this stands. Yes, it's the American Standard Code for Information Interchange. So it's something agreed. We have someone decided that the decimal value 32 is going to mean a space. And well, you have here all the symbols, and then when you go to the letter, you see that for letter A, you have decimal 97. For B, 98. This is just a convention. So this is agreed. This number means this letter. So now we are also able to represent with zeros and ones, because I know how to represent the decimal value in binary. And now I know how to convert this into text. So the aim of this part was teaching you how we can use bits in order to write text messages. So here, then the part 2, it says that we have 2 inputs. Sorry. So we have, from the same mobile phone, we have a message sent, which was this input, and a message received. So as in the part 1, we have seen that we have a program that it was encrypting and decrypting messages. And here what we do is we are going to apply that program to this message. What we are actually doing here, we are doing an exclusive OR. So what we are doing here is, first of all, if we try to decode the message, we will see that there is no ASCII character which equivalent to those numbers, at least nothing making sense. So then we assume that it's encrypted with the program from part 1. So what we do is, if this is the message that we have, then we have the encryption key. The encryption key, remember that in the first part of the program we have seen that the encryption key was this number, which if you go to the calculator, in binary is this number, and if you just use this number as the key for decrypting the messages. So the key is always the same. And then I have a message, have the encryption key, and I have the decrypted message. And then with this, I see that this decimal value is letter A, capital A. And if I decode all the message, I have this. I've been told that there was a mistake. I don't know if this is, because here in this letter it seems to be a mistake. So this is actually 0. So I will fix this. But more or less the message is clear. And then the message received, again, we have the same. We decrypt it with the encryption key, and we have the result here, and we have the equivalent ASCII character. So what we actually are doing here is, for this message, sent, we are applying the encryption and decryption key. And we are doing an exclusive OR. So what is an exclusive OR? You already saw that with Charles in the week 3. So 1, exclusive OR 1, what will be the value? 0, thanks. Then 0, 1, 1, 0 again, 0 again. And hopefully this is the value we have here. You see this value is this value here. So if I go again to the calculator with the resulting value, I paste it here In decimal is number 65. Then with this 65, I go to the table and I say, okay, 65 is capital A. And with this, I do all the rest. So this was basically the practical. Any question? Everything clear? I don't see any new questions. You have any questions regarding what we have seen this week? No? So this is everything I have for today. So what we will be doing next week is watching how we can do procedure calls in assembly, and the lab session will be also with assembly programming. Thank you very much, and have a nice end of the week.